Yes, I'm Jacob Nelson from Microsoft Research. Today I'm going to talk about a project that uses computation in the network to accelerate distributed machine learning. This is work that's been done with my colleagues at KAUST, at Barefoot, and University of Washington. The remarkable success of machine learning today has been enabled by a synergy between developments in hardware and developments in machine learning techniques. ML developers want to create new, more sophisticated models trained over more and more data. And to enable this, we develop new, faster hardware accelerators. We install these accelerators in clusters and use distributed training to exploit parallelism and speed training. But even so, training a model can take hours, days, or even weeks. And this delay limits our ability to innovate. So it's important to keep looking for ways to speed up ML training. And there's been a lot of innovation in accelerators focused on the computational parts of machine learning. In the last 5 years, we've seen more than a 30x speed up in the accelerator speeds available on cloud providers. But distributed training also requires communication. What can the network do to accelerate training? Today I'm going to talk about an approach involving P4 and programmable switches that can speed up deep neural network training by up to 300%. And I'll structure my talk like this. First, I'll go over the distributed training process. Then I'll talk about SwitchML, our approach for in-network aggregation. I'll show you its performance, talk about some future work, and conclude. So let's start by looking at data parallel distributed training. I'm talking about the most commonly used distributed training technique here for deep neural networks, which is synchronous stochastic gradient descent. In this approach, each worker has a full copy of the model that we're training. And training is an iterative process where each iteration has two phases. In the first phase, each worker node reads a sample of the data set and locally does some computation-heavy learning using its accelerators. This yields a gradient vector, which we can think of as an update to the model. But each worker has learned something different and thus has a different gradient vector, has a different update. We need to update the model using all of these gradients. And we do this by computing the mean of the gradients and then using that to update the model on each worker. Now, computing a mean is easy. We just need to do an element-wise sum of all of the update vectors and then divide by the number of workers. As we scale up the number of workers involved, we can think of this as essentially doing one addition operation per gradient vector element received. Compared to the first phase, aggregation is computationally cheap, but it is communication intensive. And you can get a better feel for that when you look at some of the scales here. The gradients are large. They're on the order of hundreds of megabytes. And they have to be exchanged for every iteration of the training process. And the computational part of the training process takes only a couple hundred milliseconds generally. And so this gradient exchange, the addition phase of which we call aggregation, is very communication intensive. And it has this sort of all-to-all communication pattern because we need all of the workers to see all of the other workers' updates. And as we deploy faster and faster accelerators, this means the network has to speed up in order to keep up. And it would be nice if we could deploy new accelerators without going and redoing our entire data center network. That would be very expensive. So is there anything we can do to speed up the network? If only the switch could help. And fortunately, programmable switches are available and are quite good at this sort of computation involving a little bit of computation on a lot of data moving through the switch. And so we take advantage of this to develop SwitchML, where the network is now an ML accelerator. SwitchML uses computation on the switch to aggregate model updates in the network as the workers are sending them. This is great. We do minimal communication. Each worker just has to send its update vector and then gets back the fully aggregated updates. But there are some challenges. First of all, switches have limited storage, certainly not enough to hold hundreds of megabytes of updates. To address this, we had to develop a streaming aggregation approach. Second, switches can't do much computation per packet. And so to address this, we partition the work involved in doing aggregation between the switch and the end hosts, having each one do what it's best at. Third, machine learning is usually done over floating point numbers. And switches, being network devices, have no idea what floating point numbers are. So to do this, we've developed a couple quantization approaches that allow us to do integer computation on the switches while keeping the model in floating point. And finally, ML frameworks normally depend on reliable network abstractions like TCP. Switches don't provide such abstractions. So we had to come up with a failure recovery protocol to ensure progress and correctness. So let's look at how SwitchML works. As I said, we developed a streaming aggregation protocol. And the way this works is we use the limited memory on the switch to implement a pool of aggregators. Each element of the pool, each slot, is able to aggregate a small number of gradient elements. In our implementation, this is 32 elements. This is what we found easy to process on the switch. And we need just enough of these slots to cover the bandwidth delay product between the switch and the worker. And the process starts, and so that just means a couple hundred kilobytes rather than hundreds of megabytes. So to do this, to do aggregation, we first fill all of the available pool slots. As each worker's updates are received for a particular pool slot, it's added to the current sum. And when a particular pool slot has received all of the updates it's expecting, it then broadcasts that sum out to the workers. That frees up the slot and tells the workers that that slot is available for reuse for further aggregation. And this process continues until we have aggregated the entire update vector. Now, to implement this, we had to divide the work between the switch and the end hosts. We tried to give each one the tasks for which it was good at. So on the switch, we're doing things that are as stateless as possible. We're doing integer vector addition with 32 elements per packet received. And then we're doing counting and comparisons to detect when a particular slot has received all of the updates that are available so that it can then broadcast. But to implement this system overall, we need to do a lot more complex things. We need to take the large gradient vectors on the end host, and we need to chunk them up into these small packets. We need to quantize the data in these vectors. And we need to detect and recover from packet drops. And so we put all of that work on the end hosts, which are able to deal with this sort of complexity. I'll talk briefly about our quantization approaches. We explored a couple different approaches. The basic idea here is just that to convert floating point to some sort of fixed point value, we just need to multiply by a scaling factor and round on the way to the switch. And then when an integer aggregated update comes back from the switch, we need to convert it back to a floating point number by dividing by the scaling factor. The first approach we tried endeavored to minimize the change in interface seen on the workers. So we actually implemented 16-bit floating point, a restricted variant of 16-bit floating point on the switch using lookup tables and ALUs. The second approach that we looked at did the quantization on the workers and then sent integers to the switch. And we did this using vector instructions on the workers. And in the version that we've implemented so far, we choose a single scaling factor for the entire network by profiling the maximum values of the gradients in a few iterations of training. Now, in fact, both of these approaches allow us to train networks with equivalent accuracy in equivalent numbers of iterations as unquantized training approaches. Which is great because the floating point version that we implemented on the switch, of course, takes a lot more resources. So the fact that we can do the quantization entirely on the end host and still get good results is great. Now, this approach is not the optimal approach. We still have to do this profiling and choose the scaling factor. And a bad choice of scaling factor, even though it's fairly resilient, a bad choice of scaling factor can reduce training performance. And so we're currently looking at other numeric representations that might allow us to train with good accuracy and with good efficiency. So now I'll talk about how we deal with packet losses. Packet losses in this system can happen in two directions. First, they can happen when updates are sent from the workers to the switch. And second, they can happen when the switch broadcasts an aggregated update out to the workers. We detect losses on the worker side using timers. And when a particular chunk times out, the lost packets are retransmitted. Now, what we have to do is make sure that an update that's retransmitted is never accidentally applied twice inside the switch, because that would give us the wrong answer. And we also need to make sure that an update doesn't arrive at the wrong slot in the switch and overwrite other people's data. And we use two mechanisms to do this. First, we track the contributions of each worker to each slot using a bitmap rather than a simple counter, because that allows us to detect and ignore duplicate packets that arrive at the switch. And second, to handle packet losses in the other direction, we keep around a shadow copy of the previous result for a slot. And that gives us a window of time where workers can request retransmission of a value that they didn't receive, and we can retransmit that previous value. We implemented SwitchML using P4 on a Barefoot Tofino, and using C++ and DPDK for communication on the end hosts. We integrated SwitchML with two different commonly used deep neural network training frameworks, TensorFlow using the Horovod communication library, and with Caffe2, part of PyTorch, using the Glue communication library. We provide the same interface that these collective communication libraries use for aggregation today. Currently, our evaluations are at a fairly small scale. We have a cluster with 8 nodes involving GPUs and 8 nodes without GPUs. These nodes have both 10 and 100 gigabit networks, and we have a single Tofino switch. We evaluated SwitchML by training 9 standard convolutional neural network benchmarks over the ImageNet dataset. And we compare this training performance with TensorFlow using the NVIDIA Collective Communication Library, or NCCL. So first, I'll show you our training performance relative to that baseline. I'm showing you the speed of training with SwitchML versus the speed of training with TensorFlow using NCCL communicating over TCP. For 9 different benchmarks on both 10 gigabit networks and 100 gigabit networks. And what we see here is that SwitchML is able to provide up to 300% improvement in training performance for some networks. In the worst case, it provided 20% training performance improvement. And these differences are coming from differences in the structure of the network. So they have different ratios of communication to computation. Now let's look at scaling. Now our cluster is not large, so we're looking at scaling for small numbers. These experiments were run with a synthetic benchmark where we're just doing aggregation over and over again. And we're comparing here SwitchML with the Glue Collective Communication Library and the NCCL Collective Communication Library. And you can see this blue dotted line. That is the theoretical line rate performance were we to be able to stream things directly to the switch with no software overhead. And so what we see here is that SwitchML's performance stays relatively constant as we go from 4 workers to 16 workers, as you'd expect, because they're all going to a switch without any sort of congestion or contention. Whereas Glue and NCCL, because they're using collective communication algorithms to do reduction, they have to do more communication as you add more workers, and so their performance decreases. You may notice that we don't have NCCL performance for 16 workers. That's because NCCL uses the GPU memory directly, and we only have 8 GPUs. Finally, let's look at SwitchML's performance in the face of packet losses. Again, we use a synthetic benchmark for this, where we're injecting uniform errors into the packet stream. And we're looking at 3 different packet loss rates. First, 1/100%, 1/10%, and 1%. 1% is, of course, absurdly large here. And again, we're comparing with glue and with nickel. And what we see here is that for very small packet losses, what we're comparing here is the ratio of the time it takes to do aggregation for a single tensor versus a system with no packet losses whatsoever. So for very small packet losses, we see that occasionally glue is actually faster than us, but it's also equally slower than us, as is nickel. As we go to larger loss rates, SwitchML's packet loss recovery mechanism works quite a bit better than the existing mechanisms involving TCP. And so that's great. Reasonable packet losses have very little impact on performance. Finally, I'll just mention a couple directions that we're looking at as we try to scale this up to deal with more production scale workloads. First of all, we've looked only at a single rack scale right now. We'd like to support multiple racks using some sort of hierarchical SwitchML approach. We also need to be able to support multiple jobs running within the same rack. And we think that we can do this easily by partitioning slots between jobs. We, of course, want better numeric representations, as I mentioned earlier. And it would also be good if we could figure out how to process more than 32 elements per packet. This is possible with recirculation. When we look at processing entire MTU-sized packets, this would give us more than 30% better performance. And so with that, I'll summarize and conclude. SwitchML uses in-network aggregation to synchronize model updates for deep neural network training. This reduces traffic volume and reduces latency, speeding up training by up to 300% on a number of commonly used deep neural network benchmarks. And scaling is good. We see that aggregation time doesn't change as we increase the number of workers. You can find lots more details in our preprint up on archive, which you can find at this short URL. And with that, I'll conclude and take questions. Thank you.
Yes. I'm not an expert in ML at all, but as far as, sometimes I read papers and they say that a lot of the kind of standard benchmarks are kind of toy or smallish benchmarks. I'm kind of curious, as the data sets grow, or do you have any feel for how this approach would scale?
Yeah, it's interesting. So we looked here at essentially a subset of the sort of jobs that we actually see trained in an environment like Microsoft. These benchmarks were all convolutional neural networks for image recognition. There are lots of other networks out there involving things like speech recognition or other things relating to language, which have very different computation versus communication trade-offs. And a lot of times right now, we see that people aren't using distributed training as much as they could be because the overheads for communication are so high. So they tend to keep things small within a single box. And so that we hope with techniques like this, we can actually enable the applicability of distributed training across more types of models.
How about another dimension, you mentioned multi-rack. How about just getting to, Tofino could have 64 servers hanging off of it.
Sure.
Yeah, things would scale.
Yeah, that would work. In the current implementation, we're also using just a single pipeline, so we would have to add a little bit of the hierarchical approach to communicate things between pipelines, but that seems reasonably straightforward and probably is doable with small modifications to our existing protocols.
Just a quick question about how I would actually deploy this. Is it necessary that my Tofino switch is kind of like the store, or can I maybe put the Tofino switch somewhere in the network, kind of treat it just like a host that's kind of an accelerator that hangs somewhere off a tor or something?
That's a great question. That's another thing that we're considering, because that would enable much easier deployment. We don't need to change the entire
exactly.
data center network to enable this sort of thing. The challenge there, I think, is that often data center networks assume that there's a certain amount of bandwidth down at the leaves of the network. And to really make the best use of something like this, you'd want to give it as much bandwidth as possible. And you can certainly do that by connecting it at a higher level of the hierarchy. The other thing that you would need to consider here, we didn't look at how this approach is impacted by congestion from other traffic. Our flow control mechanism, I think, would deal with it pretty well because it essentially keeps the aggregation running at the speed of the slowest worker. But if we were putting the switch somewhere else in the network, we'd need to explore that sort of thing in more detail.
That makes sense. Thank you very much.
More questions? All right. Thank you.